Hello class. Today we're going to be learning about alkanes. In particular, we're going to be learning about how to name them and how to draw them. But before that, let's do a brief example to illustrate why do we need these naming rules in the first place. So let's say that you have two molecules, and both these molecules have the molecular formula C5H12. If they both have the same molecular formula, C5H12, can you say that they are exactly the same? Can you say that they have the same melting points, the same boiling points, the same reactivities? Is that something you can say with 100% certainty? The answer is no, because we could draw these very differently, right? Carbon is very versatile in how these atoms can be bonded together, right? Carbon can make four single covalent bonds, and thus there are many different orientations through which that we could bond these carbons together, right? It could look like this, for example. Now, both of these compounds have the same molecular formula, the same amount of carbons and hydrogens. However, they will behave fundamentally differently in terms of their chemical characteristics. Don't get me wrong, they're not going to be too dissimilar because they are very similar in many regards in terms of their polarity. They're non-polar, they have the same molecular weight, so the characteristics aren't going to be too divergent. But as we get larger molecules that allows for more complex structures, we can find that, if we incorporate a ring structure, the properties are extremely different than the straight chain variation. So understanding the structure of the molecule is extremely important. So we need a naming system that can account for that structure. And that's what we're going to be doing today. We're going to start our journey of hydrocarbon naming with alkanes. Now, alkanes are perhaps the simplest of our hydrocarbons because they only have single carbon-carbon bonds. Now, examples of alkanes could be things like methane, ethane, and propane. Ethane is the simplest of all hydrocarbons, right? It's just CH4. Ethane is C2H6, and propane is C3H8. Now, based on what I just said, I'm sure you've seen the general formula for an alkane is CnH2n plus 2. Here, n represents your number of carbons, right? So if we had a molecule that was, say, 8 carbons, octane, how many hydrogens would it have? Well, that would be 2 times 8 is 16, plus 2 more is 18. So that'd be C8H18. How do we name alkanes, these hydrocarbon molecules that are composed of single carbon bonds? Well, there is a standard by which we do so, and this is the IUPAC naming nomenclature. Now, on my website, I have posted a naming kind of summary that goes over all of the rules we are going to learn, even a little bit more detailed than what we are going to do, but it is an excellent resource, an excellent kind of thesaurus of what we've learned. So if you ever are confused as to, okay, how do I name this again? I do recommend you check that out. Now, how do we name these? Well, the general naming rules consist of using several prefixes depending on, what types of side chains you have, things of that nature. And prefixes obviously come before the name, as well as a series of suffixes. And the suffixes will tell you, is it an alkane, an alkene, an alkyne? It'll tell you all sorts of things about the molecule. Now, when it comes to alkanes, we are going to utilize the suffix ane. Okay, so we will always use the suffix ane. And the prefix is going to be determined by the number of carbons. Now, unfortunately, there's this weird thing in organic chemistry where we actually don't use the Greek prefixes for the first 5, or is the first 4? First 4? But we do use them from 5 onwards. So you're going to have to memorize 4 new prefixes, meth, eth, prop, and bute. And then after that, we do use Greek prefixes. So for example, if we have 1 carbon, that would be methane, natural gas. If we have 2 carbons, that would be ethane. 3 would be propane, 4 would be butane, and then we enter the Greek prefixes, so 5 would be pentane, then hexane, heptane, octane, nonane, decane, etc. So the prefixes are going to be, they're going to be unique to organic chemistry for the first 4, then after that we do use those Greek prefixes. So let's go back to that problem I put on the board at the start of class. How do we deal with naming molecules that have the same molecular formulas but different molecular structures? What do we do in this situation? Well, we're not going to be using this nomenclature here, isobutane. We're going to learn a system that we can apply that doesn't require memorizing a lot of these prefixes. So how do we name these structures? How do we name them? This is going to come down to determining what your parent chain is and then labeling your side chains. So let's go through that. When talking about a parent chain, that is going to be the longest chain of carbons in your molecule. Now keep in mind, this might not be from left to right the longest. A lot of the times we get stuck in that mindset where we're looking at the molecule and we're counting carbons from left to right. Okay, look, it's 7. But you have to be careful because sometimes your branched side chains may be longer and you would have to then make that the parent chain. You'll see what I'm talking about in a moment. Now, all side branches are called substituent groups. And these substituent groups are called so because they substitute for a hydrogen on your carbon. Now, alkyl groups are alkanes that replace a hydrogen on the parent chain. So if you have a methane, right, a CH4, if it bonds to a long chain hydrocarbon, that would now be a substituent group. And we call that substituent group methyl. So they are named with the suffix YL. If we added butane onto it, right, a 4-carbon substituent group onto our, say, long heptane or octane molecule, it would have to be octane, you would say butyl. So the ones that we are going to be using are these ones here. You're going to be seeing methyl, ethyl, propyl, and butyl. I do not expect you to know these ones here: isopropyl, isobutyl, sepbutyl, and tert-butyl. These substituent groups are important when you're dealing with aromatic rings and other structures, but we're just going to avoid those in this course. Not the aromatic rings, we're going to avoid these substituent groups being bound to them. So let's name this molecule here. So if we follow the IUPAC naming rules, this molecule is named 3-ethyl 2,4-dimethyl-hexane. Now you may be saying to yourself, how the heck am I supposed to know that? Once you break it down stepwise, it's not that bad. It's going to require some practice, however. So first we need to figure out what the parent chain is. So we need to count our carbons. And if we count our carbons, we see that our longest chain here is going to be 1, 2, 3, 4, 5, 6. Now, I technically just did something wrong. We always want to label our parent chain such that our substituent groups get the lowest numbers possible. So the lowest cumulative numbers possible would be if I labeled from this end. 1, 2, 3, 4, 5, and 6. So if I number them, it's 1, 2, 3, 4, 5, and 6. Now, students always ask me, well, Mr. Salt, like, what if instead I chose this carbon here to be number 1? Well, does your answer change, or is it exactly the same? Your answer would be exactly the same. No matter what, at your second carbon, there will be a methyl group attached, right? Here, carbon 2, if we labeled it from 1, 2, 3, 4, you would find that on carbon 2 here, there is a methyl group, right? If we labeled it 1, 2, 3, 4, on this carbon 2, there would still be a methyl group. So it doesn't change your answer either way. So you want to number each atom in the parent chain such that your substituent groups have the lowest numbers possible. Next, you want to name the alkyl group substituents with their positions. So if we look here, we have 1 here at carbon 2, so that would be 2-methyl. We have 1 here, and that's a 2-carbon substituent group. That would be 3-ethyl. And then we have another one here on carbon 4, and that is 4-methyl. So we have 2-methyl, 3-ethyl, and 4-methyl are your substituent groups. Now, if an alkyl group appears more than once in your molecule, in your structure, you do need to use your common prefixes in order to indicate how many. So here we have 1 group, methyl group on 2, and 1 methyl group on 4. So that would be 2,4-dimethyl. So you do need to use di there to represent that you have 2 methyl groups in the structure of your molecule. So if you go back to the name of this molecule, that's why it is 2,4-dimethyl. So whenever you have a substituent group repeated more than once, you must use these prefixes. Next up, you want to list the names of your alkyl substituents in alphabetical order. And this does not include your prefix. So, in this case, we have M and E, E on ethyl, M for methyl. Now, E comes before M, and thus you would list ethyl before methyl in the name of your compound. So again, your alkyl substituents, if you're asking what order I need to put these in, it is always alphabetical. And lastly, you do need to use proper punctuation. This is very important when you are writing the name. We separate numbers with commas, and we separate numbers from words, and words from words, well, just numbers from words, with dashes. So commas separate numbers, and hyphens, dashes, are used to separate numbers and words. It is very important you are consistent with all of these rules. And the only way that's going to happen is with practice, which is why you do have a lot of practice questions in your booklets. Now, the name of your alkane is written as one word, and you're going to see what I mean by that in one second. So, when we put it all together, it is 3-ethyl 2,4-dimethylhexane. Notice how this is one word. Do not put a space there. So, 3-ethyl 2,4-dimethylhexane. So to summarize, find the longest chain, that is your parent chain. Number your chain such that your substituent groups get the lowest numbers possible. Write out which substituents you have at which carbons. Ensure that you add prefixes if those substituents are repeated multiple times. Next, you want to put it all together. So put your substituent groups in alphabetical order and ensure you are using proper punctuation when you do so, separating numbers by commas and numbers and words by hyphens. If you follow those rules, you will get them right every time. What is challenging is knowing when to do what, especially as we add more substituent groups to the mix. Okay, let's go over these problems. So, what do we need to do first? We need to identify the longest chain of carbons. That is our parent chain. Now, you may be tempted to do this. You may be tempted to go 1, 2, 3, 4. Is that our longest chain if we do that? No, right? No, that is not our longest chain. Our longest chain is if we go 1, 2, 3, 4, and 5. Now, I'll always get students that ask me, Mr. Salt, could we label it 1, 2, 3, 4, 5? And again, I would say to them, well, will your answer be the same either way? And the answer to that is yes, it will be the same either way, so it doesn't matter which way you label it. So now that we've identified our parent chain, what do we call that? What is our parent chain? It's 5 carbons. It is a alkane. So our parent chain here is going to be pentane. So that is our parent chain, it is pentane. Next up, we need to identify our substituent groups. We have 2 substituent groups. We have this methyl group on carbon 3 and this methyl group on carbon 3. So we have 2 methyl groups on carbon 3. 3,3-dimethyl. Now normally I would write out individually on which carbon do we have each substituent group and what substituent group it is. But here it's nice and easy, right? We have 2 methyls on carbon 3. So when we combine this together with proper punctuation, our final answer is 3,3-dimethyl pentane, all as one word. 3,3-dimethyl pentane. Now, what about this molecule here? Again, let's quickly go over it. What is our parent chain? Here you have a lot of options as to the way you number it. And again, all of them give you the exact same answer, so it doesn't matter which way you do it. You can label it from left to right here, 1, 2, 3, 4, 5. You could label it from right to left, 1, 2, 3, 4, 5. You can go like this, 1, 2, 3, 4, 5, or like this, 1, 2, 3, 4, 5. All of those will give you the exact same answer. Okay, so it's key here that you have a little bit of spatial awareness, and you can see that it honestly doesn't matter which way you label it. Your substituent groups are going to be on the exact same carbons either way. So, for simplicity's sake, we'll label this 1, 2, 3, 4, and 5. What is our parent chain? Well, our parent chain here is going to be, again, pentane. But this time, we have a couple more substituent groups. We have 2 methyl groups on carbon 2. So that's 2, 2. You know what, we're going to make it easy. I'm just going to put 2 methyl, 2 methyl, and then we have 2 methyl groups on carbon 4. So that's going to be 4 methyl, 4 methyl. Now when we combine this all together, it's going to look a little messy, but it is 2, 2, 4, 4 tetramethyl pentane. So again, since there are 4 methyl groups, we do use that prefix tetra. Let's do one more example. Here I've drawn a molecule, and it's a little bit more complex, and it's going to draw on some of those more obscure rules that we talked about. So first things first, we do need to label our parent chain. Now, our longest chain here, you may be very tempted to do something like this and say 1, 2, 3, 4, 5, 6, 7, but that would be wrong. Why is that wrong? Right, this is where we got to look and really ask ourselves, what is the longest chain of carbons? It's not straight from left to right. It is going to be right here, like that. So it is 1, 2, 3, 4, 5, 6, 7, 8, and 9. Now, if you didn't see that, that's okay. It's going to come with practice. But our longest chain is this right here. So what is a 9-carbon chain called? What is our base name, our parent name? Well, our parent name is nonane, 9 carbons long. And now we have to figure out, okay, where are our substituent groups? Well, we have one right here on carbon 3, one right here on carbon 5, and one right here on carbon 6. So what are our substituent groups? Well, we have 3 methyl, we have 5 methyl, and we have 6 ethyl. Now, you might be asking yourself, is this the lowest numbers possible for our substituent groups? And I'd say that is a very good question. Are our numbers cumulatively lower if we count in the other direction? So if we count this way, it'd be 1, 2, 3, 4, 5, 6, 7. So that'd be 4, 5, and 7. And if it's at 4, 5, and 7, 9 plus 7, 16 cumulatively. Whereas labeling it this way is 3, 5, and 6. That is going to be 14 cumulatively. So we do get slightly lower numbers if we label it this way as opposed to the other way. So I know somewhat of an obscure rule, but it is important. All right, so let's combine this together into a name. So when we combine this together, what comes first? Ethyls or methyls? Again, it should be alphabetical order, so ethyl comes first. So we will say that this is 6 ethyl. And then we have 3, 5 dimethyl. nonane. So take the time, do the practice, and this will get easier, I promise. Okay, so we've learned how to name alkanes. Now let's discuss how to draw hydrocarbons. Luckily, in my opinion, this is way easier because the name literally tells you what the structure is. And a lot of the guesswork is taken out as a result. So first up, you do need to identify that parent chain. You look at the end of the name, right, and you identify that parent branch. If it's decane, for example, that's 10 carbons in a row, and you don't have to do any fancy guesswork like you had to do with naming, right? You don't have to zigzag and try to find the longest chain. You can just draw them straight left to right, because you are deciding what that chain is going to look like. So draw out your chain, and then you need to number it. And then on your appropriately numbered carbons, add the substituent groups that have been listed in the name. That is it. So when drawing them, it is quite easy in my opinion, but there is one mistake that students always make. How many bonds can carbon form? It can form 4 bonds, right? It can form 4. So if it can form 4 bonds, why is it that students always tell me I have CH2, I have 2 substituent groups off of it, and both carbon, and our carbon is bonded to 2 other carbons in our parent chain, right? Students will often tell me I have 6 things bonded to that carbon. So it's very important that you double check. Make sure each of your carbons only has 4 bonds, right? If it has more than that, well, it'll eliminate some of those hydrogens. If it has less than that, add some hydrogens, right? We got to add hydrogens as needed. So let's do an example. 2,2,4-trimethylpentane. What is our parent chain here? It is pentane. And if our parent chain is pentane, how many carbons am I going to draw? I am going to draw 5. So here I'm just going to space out and draw 5 carbons. Next up, we need to number them. So we have carbon here 1, 2, 3, 4, and 5. We will next add our substituent groups, and we have 2 methyl groups on carbon 2, right? It's 2, 2. So we will draw 2 methyl groups here on carbon 2. We have 1 methyl group on carbon 4. And then lastly, we do need to add the appropriate number of hydrogens. And again, this is where students often make mistakes. They will try to do everything all at once, and they will often do this. They just put CH2 for all of those carbons in the middle. Now if we look, why is that wrong? Well, this carbon here now has 1, 2, 3, 4, 5, 6 bonds. It can only make 4 bonds, therefore you need to do that, right? There is no other hydrogen bonded to this carbon. Here, this carbon now has 1, 2, 3, 4, 5 bonds. It only needs 1 hydrogen, okay? So drawing them is quite simple because the name tells you exactly how to draw it. You just need to be careful of that one caveat, which is each carbon can only make 4 bonds. Right on, that is all for today. Have a wonderful day, everyone.